Okay, so we have the pleasure to have the third lecture by Subir today. I think Subir is going to finish the connection between gravity and SYK, and then he'll move on to fermions moving in gauge fields. Is that correct?
Hopefully, yes.
Hopefully. Before we start, I just want to make a very brief announcement. So, as you know, we're having this workshop on June 2nd and June 3rd. I guess some of you may want to attend. I want to make a short announcement which is especially geared at doctoral students, doctorants, PhD, and perhaps also postdocs. On the first day, there is a lunch which is organized for the speakers only, but we'll still have about 10 spots for other participants, and I would like to give a priority to doctoral students who may want to have lunch with speakers. So on June 2nd, just, if there are about 10 PhD students or postdocs who want to come and have lunch with us, just come and line up and we'll take the first 10. And then on the second day, the lunch is for all participants. So just wanted to say that. Okay, but then without further ado, the floor is yours.
All right, thank you, Antoine. As Antoine said, I want to finish up the discussion of the SYK model and the connection to charged black holes today. And then just to get an overview of where I want to go. So Antoine has already discussed how you can go from the SYK model to the TJ model today, and shown how you get, in the early treatment of the TJ model, a bad metal regime. Then it turns out that the TJ model also, under different treatments that I'll mention briefly today, and I think Antoine will say more about next week, you can also get a strange metal in the TJ model. All right, so that's all very satisfactory, but this is all in the context of models which are effectively in high dimension. These are all large dimension models in one way or the other. And the question we're always asked is, well, what about 2 dimensions or lower dimensions? Can all of this work in lower dimension? So one way to go to a lower dimensional model was also mentioned briefly by Antoine. You make a lattice of SYK models and study that. But as he also mentioned, that leads only to bad metal behavior. It doesn't give you a strange metal. So what I'd like to address, and this will be really what I'll focus on in my last lecture, is can you get a model of a strange metal in 2 dimensions? There hasn't really been any, but in very recent work, we think we finally have one. And it is also connected in a way to SYK models, but a different class of SYK models, which I'll introduce at the very end of my talk today, if I plan things correctly. Okay, so we have a discussion of the comparison between SYK model and charged black holes. And last time I gave a discussion of where this linear T term came from. And I argued that you should think of the SYK model as some kind of conformal field theory, which is perturbed by some operators, O sub h of dimension h, so that the 2-point correlator of the operators in the conformal field theory decays as 1 over tau to the h. So this kind of perturbation by this formally irrelevant operator will give you corrections to all observables, including the Green's function, the entropy, and the power laws that appear here can be deduced by simple scaling arguments. So now the task is simply to determine the allowed values of h. Okay. So you can look at the 3-point correlation function between O sub h and the fermions. And in the large N limit, if you're assuming O sub h is some fermion bilinear, you get an integral equation given graphically by this. And then I argued that in the scaling limit, so this is like a linear integral equation for this vertex. And this is like a source term. And depending on the source term, you will get many different solutions, which depend on the nature of the source term you put in, which is the UV operator that you put in for O sub h. We're not interested in all of those terms. We just want to get the eigenterms, if you wish. And the easiest way to get them is to just drop the source term because it's much smaller in the long time limit. You can check afterwards. And just look at the homogeneous equation. Now this is very much like an eigenvalue equation where E has to equal 1. And this equation turns out to be possible to solve exactly. So this vertex operator is this 3-point correlation function. And this is then this eigenvalue equation with this kernel, which is like a matrix, which is known exactly in terms of the conformal Green's function. OK, this is a way too complicated equation to solve. But it's sufficient to just solve it by taking tau 0 to infinity. So therefore, you just need to make an ansatz on what the behavior of V is when tau 0 goes to infinity. And this is where I messed up a little bit. I just forgotten how this all worked. So the point is that in that limit, we can use the operator product expansion. So what happens here is that, look at this vertex here. When tau 0 goes to infinity, so imagine that's going off really far away. That's equivalent to these 2 points, tau 1 and tau 2, where there are fermions coming close to each other. So you can imagine these tau 1 is approaching tau 2. And so that you have these 2 fermion operators as tau 1 and tau 2, and they're approaching each other. And that's exactly what the operator product expansion tells us happens. So you think of these 2 operators as merging into a single operator. The leading term is as the unit operator, which decays by the Green's function. But then there can be other operators. Again, in fact, there should be these other operators, O sub h. And then you can figure out this power law here just by scaling. So this is dimension h. You can just figure out what this dimension has to be. Then you insert this OPE into the 3-point correlator. There'll be some correlator of the 2 O sub h's, but that depends on, there's O sub h of tau 1 going to tau 0. And tau 0 is so large that just gives some prefactor of tau 0 we're not interested in. We're only interested in the dependence on tau 1, 2. And so from this, you conclude that when as tau 0 goes to infinity, this decays in this manner. This is what I had written down last time. I didn't have this OPE derivation. All right, so now you know the behavior of V on tau 1, 2. You just go back and insert it, insert it into this equation and do the integrals over tau 3 and tau 4. And you find that the equation is indeed satisfied. You get the same function of tau 1, 2 on the 2 sides. And put E equals 1, and then you get a condition on H. So that's how you get this very famous equation right here for H. It's just a matter of doing those integrals now. And there's really quite elementary integrals. So I've given you all the information to get this tan pi h over 2 minus pi by 4. Well, they're not elementary. You have to look up Grashstein and Rijik, but anyway. So from this, you get that the leading operator is H equals 2. And that gives you the linear T correction. All right. So now, so in fact, this we can test it numerically. This is work done by Maria Tikhanovskaya and Hayugo and former postdoc Risha Tonopolsky. So the red line here is the dynamic spin susceptibility obtained by just solving the equations that Antoine has already put on the board. You've seen many times by this point. So you have G is 1 over I omega minus sigma of omega, and sigma of tau is minus J squared, G squared of tau, G of minus tau, and chi of tau is G of tau, G of minus tau. So this is these equations you put on a computer and you solve to high precision. Take a Fourier transform, and you get the red line shown here. OK, so the leading term here, the sine omega, this is the marginal term that Antoine was mentioning. That just comes from this 1 over square root of tau behavior. So the leading behavior is, G of tau goes as 1 over square root of tau. So this tells us that this goes as 1 over tau. Take a Fourier transform, that gives you the sine omega in the imaginary part. So that's the leading behavior. So that just gives you the fact that this goes to a constant. But the entire frequency dependence now comes from the corrections to scaling. So this kind of OPE expansion, how you and others have carried out to some really high order, to order omega cubed. There's only two fitting parameters here, which you can check with other methods. And that leads to this dashed line. So this dashed, this is very annoying. This dashed line over here is this asymptotic expansion. So the leading term, mod omega term here, is coming precisely from, is exactly the same leading term that gives us the h equals 2. The h equals 2 operator gives you this mod omega term, and that's by far the most dominant one, as you can see from the plot. And so in a way, you can think of this, as I'm going to relate this h equals 2 operator to a graviton, you can think of this linear dependence as an observation of the graviton in the solution of these equations. Okay, so who knew these equations have a graviton in them? Okay, well that's solving these large n equations, but what about SU2? So you take the SU2 model, and I think Antoine will say more about this next lecture. This is just the insulating spin model, SI.Sj, and numerically compute the same quantity chi double prime of omega. And what you get from that is this green line from the numerical computation. And if you know what this has is a big peak at low frequency. That is due to the presence of spin glass order. But when you go to finite frequency, it fits the large n solution with this linear omega dependence, very well. There's one fit parameter, which is just the frequency scale. The integral under both curves is fixed to be whatever it has to be. And you can see that it's not so bad at all. So this is rather encouraging indication that in the SU2 model, the physical model, with the infinite range interactions, even though there's spin glass order, if you go just a little higher in frequency, there seems to be the spin liquid behavior, this linear omega behavior that you saw in the m equals infinity model. So the m equals infinity model is not as far as you would think, the SUM model from the SU2 model. Okay, so yeah, so that's the, so this is really, if this is the interpretation correct, which I believe it is, then this is observation of a graviton, at least in the fully connected spin model. So we can also ask what happens when you extend these equations at m equals infinity, and how do you get this little peak over here? So this is something my student Main Christos and Felix Hale looked at. I'll very briefly just mention their results. Basically, these same equations that I wrote down over here only require one additional term, which is this QAB. And that's the Edwards-Anderson spin glass order parameter. Determining QAB requires more analysis, which you can read our paper about. And what you find from that analysis, something that had already been pointed out in the GPS paper, that this QAB becomes non-zero below a temperature which is e to the minus square root of m pi. So as m goes to infinity, the spin glass order disappears, but at finite m, it's present at any finite m. But even for m equals 2, you now see my most favorite number, e to the minus square root of 2 pi, which is quite a small number. And the smallness of this number a posteriori is our understanding of why even in the SU2 model here, you're seeing the m equals infinity graviton behavior. It reappears at higher frequencies, even though the spin glass order at low. So in these equations, this QAB is determined by finite m corrections. But now you can look at the feedback of the QAB on the fermion-Green's function. And this turns out to be rather similar to the Fermi-liquid crossover that Antoine described this morning, where you had a hopping term to the J model. Here, the spin glass order for the pure J model also has a very similar effect. And when you solve these equations, what you find is that this dynamic spin susceptibility, this is the final answer, has a delta function at zero frequency in the infinite size limit, proportional to the spin glass order parameter. And then a regular function, a regular crossover function, Antoine had a function of omega over EF star. Here it's essentially the same function, omega over this Edwards-Anderson order parameter. And these are the functions from numerical solutions. So this function here is presumed to describe this behavior. If you subtract out the delta function, there's a regular part left over, and that's what that function is describing. I think I'm going to get rid of this. I'm not comfortable with it. Okay. All right, so now then I also started, so that's all coming from this term here at the n equals infinity theory. Then we haven't thought about 1 over n correction. These are finite size corrections for any SUM yet. So what I mentioned last time, there's a universal correction, this -3/2 log of temperature. And now I'm going to give you an indication of where that comes from. I should say my lecture today will be more like a seminar. I do want to finish all of this and transition to the finite dimensional systems. But my last lecture will be, I think I'll go back to a little more pedagogical treatment on the board. So, the technical details of gravity, I'm sure you don't want to know. And the technical details of this are also quite complicated, but I'll give you a sketch the basic argument. Okay, so this is something I showed last time. You start with the SYK model. You average over the interaction U. You get this exact path integral. Then you insert the identity 1. And then you do the integral over the fermion. And ignore the off-diagonal replicas because we are not going to be in the spin glass phase. And then you get this exact path integral for the SYK model, which is expressed as a path integral over 2 bilocal fields. Okay, so you have this very huge space. That's, I'm just drawing a 2-dimensional section of it. Say this axis is g of tau 1, tau 2, and you have sigma of tau 1, tau 2. So you're integrating over all of this space, and your first step is to find the saddle point. So you look for a saddle point. Let's call that GS and sigma S. So this is the action, delta sigma S is equal to 0 at sigma S. And similarly, delta S, delta B. Okay, these two equations give you exactly these equations here, just written in a different way. You can check, you start with this action, and you take those derivatives, you'll get back to these equations. Okay, so everything I've told you so far are properties of these equations. But now we want to go away from this point. We want to move away from it. Now, this is obviously a really complicated problem because you have 2 bilocal functions. And so we're going to do what you normally do in field theory when you do the nonlinear sigma model. You're going to try to move along the flat directions. You want to move around directions where it's not going to cost you any action. So we're going to move along a very special valley. So this is some valley here. So this is a valley in the action. And we're only going to integrate along the valley, okay? Because all the other ones, the other directions we assume don't give you any singular corrections. So we want choose the valley correctly. And this will be parameterized. This valley will be parameterized actually by a single function I call f of tau. So this means that there's a Green's function. I'm along this valley. As I move along this valley, we'll see that g is given by the action of the function f of tau. It sort of kind of acts onto g sub s of tau. And similarly for sigma. So if you give me an f of tau, which some coordinate along this valley, any function f. So this is, this is still a functional integral. I'm drawing it as a one-dimensional line, but it's a set of all functions f of tau of just 1 time tau. So given the saddle point value and this function, I get some g. Okay, and I'm going to choose this f of tau carefully so that this costs me hardly any action. The action doesn't change. Okay, so what f of tau should I choose? Well, the answer's on the board. There's also actually another gauge transformation, which I'm just going to ignore. It goes along for the right. It's important for many things, but let's keep life simple and just focus on the f's and not the little g's. So what action am I going to choose? Well, what I do know is that if I ignore this term in the action, okay, so if I ignore this term, then I know a regime where the valley is exactly flat. So this, the valley, so the exactly flat valley, when you just ignore, you have this trace log, and you have this d by d tau term minus mu times some delta functions, and you have a sigma. So basically, if I drop this term here, then you can see that for any f of tau, the action doesn't change. And you can check that. It's very similar to the asymptotic low frequency analysis that Antoine mentioned. It's equivalent to just dropping this term, which is something you always do in the low frequency limit. This goes as square root of omega, so you ignore this. So since you can ignore this, correspondingly, you can ignore this. And when you ignore it, then you find that this path integral, and this is pointed out by Kitev, there's an exactly flat valley. But this action is exactly the same along this valley when you drop this term. Okay. Now this is sort of like in a ferromagnet when you're doing a nonlinear sigma model. If you have perfect rotational symmetry, you have some ferromagnetic saddle point, and then you say the exactly flat valley is basically when I rotate all the spins by the same angle. That's an exactly flat direction. Here also there's an exactly flat direction, but it's not just a global rotation. It's not SO3 or something like that. It's not a finite dimensional group. It's an infinite dimensional group. It's a set of all function f of tau, and these functions have to obey. So they have to be monotonic, and if you have finite temperature, they're on a circle. So the symmetry of this valley, or flat valley, or it's not the symmetry, it's what the space is. The flat valley is the space what mathematicians call diff S1. So this is the set of differentiable functions that map the circle back to the circle monotonically. So that's a huge space. It's not just a finite dimensional space like SO3. And that's the direction of this flat valley. All right. Okay, but it's not exactly flat, all right? It's not exactly flat because this term is not 0. So any action here along this valley is going to be then given by corrections from this term, meaning it's going to come from these operators O sub h. There are other operators that are correcting this conformal theory, and it's going to come from those operators. And so we're just going to write down, we're just going to make a guess as to what the effect of these terms are. Okay. So for example, if I go back to the nonlinear sigma model story, if I have a ferromagnet, then I have exactly flat direction of all possible rotations. But suppose it's not exactly flat, that there's a small anisotropy in the spin, and the z direction is preferred from the x and y directions. So then you will say, aha, there should be a term in the action which is sz squared, which just tells me that if I'm plotting around the z, I gain a little bit I have to pay a little energy cost. That's the easy plane direction. It depends on the sign of sz squared. So just add some leading term that lifts the degeneracy of the valley. And in the ferromagnet, you deduce that term just by symmetry arguments. You don't need to know the microscopic Hamiltonian. You just know you have a symmetry that's weakly broken, and so you just write down the simplest term that breaks that symmetry. Okay? So that's exactly what we have to do here. we have a symmetry, diff S1, that's weakly broken, and so we have to write down some function that breaks diff S1. But there's another thing I have to keep in mind, which is the following. If I'm doing the theory, again, going back to the theory of the ferromagnet, yes, if I have a uniformly ordered state, then the order parameter space is SO3, all possible rotations, but there are certain rotations that don't move me. There's a rotation about the z-axis. That doesn't change the state at all, okay? So now I have to ask, is there any subgroup of diff S1 which doesn't change, in which this transformation is trivial? You apply a certain f of tau to G sub S, I'm just going to get back G sub S. Are there any such transformations in which the f of tau has no action on G sub S? So this means without f of tau, you don't even move. There's certain f of tau, you don't even move from this point. You just stay right there. Just like in a ferromagnet, if I rotate about this axis, I don't move from the point where I'm at, okay? So what is the stationary, what are the special f of tau where I stay at exactly at this point? Well, so that's, you pick some f of tau. So the question I want to ask is, given G is G sub S, for what f of tau does this give me back the same G? All right, well, the answer is right here. So G sub S, the saddle point value at long times, has this behavior, 1 over tau 1 minus tau 2. And now I invite you to verify that if any f of tau of this form, if I take f of tau, which is A tau plus B and C tau plus D, this is the group SL2R, really B SL2R, where AD minus BC is 1. So any f of tau like this, you can check that this action is trivial. So this action here is the action of f on G sub S. And so the most important, another very important point here is that G sub S is equal to, if I take the function A tau plus B over C tau plus D, and this circle is this complicated action acting on G sub S. This is true. This is a correct statement only for this set of f of tau. So one set of this is kind of trivial to see. If I put C equals 0, then this is just time translation, obviously true. This is rescaling of time, which is also true, you can check. Though the non-trivial one is only the 1 over tau one. If you ignore these two, 1 over tau, that also works, and that's the special conformal transformation, which is also a symmetry of this scale invariant behavior. So it's that extra special conformal transformations that we hadn't used before, but it's very important here. So this tells me that the action along this valley is like a nonlinear sigma model on diff S1 slash SL2R. Okay, just like the nonlinear sigma model of ferromagnet is SO3 slash U1. It's exactly the same thing. Okay. All right. So the action is not 0 here because of this term. So basically now, but this term is a high energy term. So what I want to do now is the following. I'm going to take this high dimensional path integral, which is integral over G and sigma, and convert it to a one-dimensional path integral. I'm only going to integrate along this valley. Again, ignore the phases. And this four-dimensional, functions of 4 times now becomes a function of just 1 time of f of tau. So it's a big reduction in parameter space. In the ferromagnet, it's like ignoring amplitude fluctuations. So we ignore all of that. And then you just have a function f of tau, which is this function here. So now what we need is the S effective. So along this valley, there's some S effective, which I need to figure out. All right, so this is where the hard part comes. Actually, that can't be done exactly, even for the SYK model. There's a large Q SYK model where that can be done exactly. But that's further approximation. If you want to, but we can make a lot of progress by just using symmetry. So you want some S effective to also obey this property that the action, that whatever S effective you write down recognizes this. So the action, change in action has to be 0. So you want S effective S effective of A tau plus B. So f of tau, if I take f of tau equals A tau plus B over C tau plus D, that must be equal to 0. Okay? And there has to be some function of derivative of f of tau. And so it should be an expansion in epsilon of tau and its derivatives. Where f of tau is tau plus epsilon of tau. So f of tau equals tau is doing nothing. But now you imagine that there's some correction to it. And so you want some functional of epsilon of tau, or f of tau equivalently, which has this property. Okay. All right, so the simplest function that does that is precisely the Schwarzian. Oops. This is for finite temperature, let me ignore that. So there's the answer. Is this function here? That's the Schwarzian. G Schwarzian tau is this function. And you can have a lot of fun checking that if I put G equals A tau plus B of C tau plus D, that gives you exactly 0. And this is really the only thing. Okay. So there's the action. Again, ignore this. This has to do with the phase fluctuations. There's this part here, which is, now I've gone to finite temperature by a conformal mapping, and then you get a tangent of pi tau f of tau, the Schwarzian of this, with a coefficient gamma, which I don't know. So this is just like saying, when I have a ferromagnet, there's a stiffness, which you don't know what it is some or superfluid density for a superfluid. You don't know what it is in terms of the microscopics, but you know it's a number that characterizes the infrared theory. So this one number, which is this coefficient gamma, that characterizes the nonlinear sigma model along the valley.
So
yeah.
You are saying that for the SYK model,
yeah.
there isn't a microscopic derivation of this action apart from the symmetry argument. When can we compute that action?
No. Yes, you cannot. You have to. I mean, you cannot compute gamma. That's the precise statement. I actually come to think of it, I don't think anyone's actually computed the full action starting from the SYK model. What you can try to do is you take this Schwarzian and write f of tau as nearly trivial, make epsilon small, and so then the Schwarzian of f tau, I forget now, the leading term is something like epsilon tau squared or something like that. No, prime tau, something, that's the leading term. So there's a coefficient here that you can try to get. So the best people have done is try to get this coefficient. And that, the reason it's so hard is that you really have to treat this term. You have to go beyond the scaling limit. It all depends on this term. And we don't have any exact results on that. I gave you the only exact result you have, which is the computation of the h equals 2, the allowed values of h.
How do we know this is the only term, that there are no other terms?
Well, you can take the square of the Schwarzian and other terms like that, but they have more derivatives. This is the simplest term with the fewest derivatives. Yeah, exactly like in this sigma model. Now, the sigma model, also has an infinite number of terms because it's, grad n squared. Yeah. In the sigma model, you have the constraint n squared equals 1, which you write as pi times square root of 1 minus pi squared, and then you get an infinite number of terms in terms of pi. That's exactly what I'm doing here. This epsilon is like the pi, and then you plug this in here, and you get an infinite number of terms in epsilon. And they have to be there just by this requirement of this. Just like all the infinite number of terms here, in terms of pi, have to be there by rotational symmetry. Okay? So it's the conformal symmetry of the saddle point, which is this SL2R group, SL2R is the conformal group in one dimension if you continue it from higher dimensions. It's a conformal symmetry that tells you it has to be this small. Yeah. So the value of gamma has only been determined numerically. So how would you determine gamma? Well, the simplest is to compute the entropy. So for example, now, suppose I want to just, this term actually already has a contribution even at n equals infinity. So if I just put tau equals, f of tau equals tau, and you evaluate this last term. So for f of tau equals tau, so basically you take the large term, which is gamma over 4 pi squared, tan pi tau, comma tau, evaluate the Schwarzschild, and if I remember this right, it's minus gamma t squared over 2. That's why the 4 pi squared was chosen for this to work out. And this gives you then, this implies, after all, that S is S naught plus gamma t. So this gamma here is exactly the gamma here, which is why I, of course, called it the same symbol. So if you want to numerically compute the coefficient of Schwarzschild, what you numerically do is actually compute the entropy, which is what people have done. All right. So now you have a path integral, which I've written down here. So it's a path integral over all functions f of tau, which live on diff S1. So these are all monotonic functions that map the circle onto the circle. And you have to mod out by the SL2R. Now, SL2R is a non-compact group, so that modding out is very important. It's an infinity that you have to take out. This is an infinite volume, and you have to mod it out and do this path integral. Amazingly, this path integral can be done exactly with no further approximation. That was shown by, well, I have not written it down here, Witten and Stanford. A beautiful paper. We use all kinds of very sophisticated, well, I mean, they use for the Popper methods, you use introduce a Grassmann field to get the measure of SL2R, and then you use the Dustemer-Heckman theorem. There's some very powerful theorem of such path integrals, which tell you that these integrals are Gaussian exact, that you just take the Gaussian approximation and do the Gaussian function integral, which we all know how to do. In this case, that's not so bad. It can be done. And in the review article I've written with Antoine, there's an appendix that shows you exactly how to do it. But the more non-trivial statement is that there are no corrections to the Gaussian path integral. And there are certain very special action for whether that's true that I don't fully understand this at all. But anyway, so you can look it up. So you do this path integral exactly, and lo and behold, that's what gives you this minus 3/2 log t. And this 3 it's related to the fact that SL2R has 3 generators, just a count of the number of zero modes. Each zero mode gives you a minus 1/2 log. That's the quick way to see the answer, which Witten just states in one line in the paper, so it took me many months to understand what he was trying to say, but okay. Anyway, so that's it. So that's the route to getting the minus 3/2, and also knowing that there are no further corrections. Now, that's also actually very important, the fact that there are no further corrections to this path integral. So now what you can do is you can take the so what we have computed schematically is df of e to the minus the Schwarzschild, some gamma Schwarzschild of tau. That's the action. We've done this full path integral, and now we want to invert it. So this is a function only of temperature. That's the only, well, and there's a parameter gamma there. It also depends on temperature. So I want to now invert this. I want to write this as dE dE, d of E, e to the minus E over temperature. So once you know z of tau, you want to determine d of E, and that's like an inverse Laplace transform. Now, normally you would never trust an inverse Laplace transform if you had an approximate answer here, but since you have the exact answer, you can do the inverse Laplace transform, and in fact, it gives you exactly the fact that the 3/2 is totally crucial, a very simple integral in the end, and this is the answer. So you give this sinh square root of 2n gamma e that comes from inverting. In fact, the way to do this is to put in here, dE, put in sinh of square root of 2n gamma e, e to the minus e over t. Mathematica can do that integral, and it turns out to be 1 over temperature to the power 3/2, and that 3/2 is what you get from here. Okay. Yeah.
Again, is there a simple way to see the 1/3 response without?
No, that's very complicated. That is in the paper that I wrote with Kitaev, my only paper with Kitaev more recently. And there's a whole section on that, getting the n to the 1/3 there.
But it will come from the Schwarz integral.
It comes from the Schwarz. That has to do with normalizing the path integral over density, number of, yeah. When you have a conserved quantity, like the total number, then the dependence on n becomes quite subtle. It has to do with that phase integral that I didn't discuss.
If I look at the right column.
Yes. Yeah, that's my next topic. Yes, go on. All right. So now we're going to look at the right column. And here, unlike the SYK model, we can actually get, starting from Einstein gravity, the exact value of gamma and the exact coefficient of gamma. We can just work it out because here what's going to happen now, just schematically speaking, is something very similar. You have a Einstein action, and again, I will forget the gauge field because that just goes along for the ride mostly, but is important for certain things. So you have an Einstein action of g mu nu. So and this g mu nu is in 3+1 dimension. So it's a 3+1 dimensional field. And we're going to reduce this to an action, which will be the Schwarzian, of just one field, f of tau. So this is 16 fields in 4 dimensions, and we're going to go down to one field in 1 dimension for the low energy theory. This reduction is very similar to the reduction here. You had 2 bilocal functions map onto one function. And what's good here, you can actually do everything explicitly. But again, it's the symmetries, as you see, turn out to be very, very similar. And that's why you get the same action. And a lot more. So we think there's more to it than just symmetry. It's really, the left-hand side is a fully quantum realization of something where there is no quantum mechanics really. On the right-hand side, you're just doing a path integral without defining a Hamiltonian. Anyway, so where are we? So let's go to doing the same thing on the right column. So let me just quickly recall my first lecture. So I'm going to, where I derived this term, the leading term. That came from the Einstein-Maxwell action with the charged black hole solution. And then at low energies, you found that, So if you just solve this and get the thermodynamics, you can get this term. Now you go to low energies, and I'm going to try to show you how you get this term here and this term here. So you take the low energy limit of this theory, and the low energy limit, the metric became this metric of ADS2, and a transverse direction, which is the angular direction of the sphere that you can neglect. So this already is, you've gone from 3+1 to 1 plus 1. So you go through an intermediate step where you have a theory on ADS2. This is called JT gravity, which is 1 plus 1. And finally, you go to 0 plus 1. Okay. So here's the picture. So now think of this, this is the black hole horizon, and this is far away from the black hole. Think of this as energy scale. This is high energy, this is low energy. So at high energy, you have 3 plus 1 dimensional space-time. At low energy, you go down to 1 plus 1. And so now you need an action to do, you do a theory in 1 plus 1 dimensions. So you derive the action. That's the easy part. You can do that exactly. And I'll show you how that's done. And then finally, you have to do the path integral from 1 plus 1 to 0 plus 1. And that also turns out to be exactly doable because of all the symmetries of ADS2. The gravity on ADS2 turns out to be rather simple. Okay. So that's the root, and I'm just going to, so here's in words, you start from 4-dimensional space-time, go down to 1 plus 1. Then you can start with the Einstein-Maxwell action and get a theory in 1 plus 1, which is sometimes called JT gravity, although there's additional terms here from the gauge field. And then you compute the saddle point fluctuations of the ADS2. All right, so this I'll be somewhat rapid because, it's gravity. This is really a lot of gravity, which I doubt this audience has that much interest in. But just to sketch the argument, so there's all of these steps are worked out in detail in a paper that I've written in 2019, sorry. So first thing you do, this is like a Kaluza-Klein reduction. You go from 3 plus 1 to 2 plus 1. 1 plus 1, excuse me. So what do? Well, you have a 4-dimensional metric, that's ds squared. And you take the angular part, and you just say, well, ignore all dependence on angles. Then there's a 2-dimensional metric, which is along the time and the radial direction. So, go back to this picture. This part, we just assume it just remains a sphere and doesn't fluctuate, the omega-2 part. There's time, and there's zeta. So there's some metric in zeta and tau. We just call that ds2. Then there's an overall scaling factor, the prefactor here, which you can think of as the radius of the horizon. That's allowed to fluctuate. It's like the zero mode of the horizon. That's allowed to fluctuate. And you can always choose your gauge to make, and this is a convenient gauge choice, to put the phi here and phi squared there. So this is just exactly what Kaluza-Klein did. Kaluza-Klein had a 5-dimensional gravity. They just, by hand, reduced it down to 4 plus 1. And they found that the 5-dimensional metric tensor became a 4-dimensional gravity plus a gauge field. So here, what do we find? We take 4-dimensional gravity. They go down to 1 plus 1. We get gravity in 1 plus 1 plus a scalar field. And that scalar field is phi. So it's not pure gravity. It's gravity plus a scalar field. Just like in Kaluza-Klein, you had a gravity plus a gauge field. So you can figure out the action for this phi and the metric. H is now the new metric. So this is what the action is. There's the famous Gibbons-Hawking term. And then finally, you can also take the low energy limit of that action. That's really what this is. And these two terms are what's called JT gravity. So what you notice in this is that the scalar field, which is the fluctuation in the radius, comes linearly. And we assume there's an I out front. So this is like a Lagrange multiplier field that appears in slave boson theory. It's linearly the I lambda times a constraint. So what you see here is that when I take the radial fluctuation into account, I get a constraint. And the constraint is this equals 0. And the solution of that constraint equals 0 is ADS2. That's just a uniform metric of negative curvature. So the bulk part basically is trivial. Here, the action is only the constraint in the bulk. That's the beauty of it. There's nothing else. There's only a constraint in the bulk. And the constraint tells us that the metric is ADS2, and you can forget about the bulk. So that's how you go from here to here. the bulk becomes totally trivial. It's just rigidly a uniform negative surface curvature ADS2. And so what's left over? What's left over is the boundary, just like in the first lecture where the entropy came entirely from the boundary, the Gibbons-Hawking term. So there is something left on the boundary. And that was the picture I drew here. There's a boundary between 1 plus 1 and 2 plus 1 dimensional space-time. And that boundary has some fluctuations. So this is the part I'll skip. You can then go in and compute the action on this action on the boundary in great detail. And here you explicitly get, and I have worked this out in gory detail, the Schwarzschild action. You get the full action, including the coefficient, which is this value here. And then, it's exactly the same theory. And therefore, you can declare victory, and from the value of gamma, you even get this result. So in this form, actually, this result has never been written down anywhere. Since you know the value of gamma, you know exactly the correction to the density of states of a black hole, charged black hole. Okay. This is for Einstein gravity. Now, of course, the string theory probably at even higher energies, and that may, that'll give you higher derivative terms at low energy in Einstein gravity, and that will change these coefficients. But if I ignore all the higher derivative terms, then this is the answer. Okay. All right, so I think that's all I want to say about gravity. But yeah, so why is this the Schwarzschild? I guess here the fact that it's a Schwarzschild has to do with the fact that the isometry group, which is very much like this, the stationary point, this transformation for the saddle point. Now if you take ADS2 and do a coordinate transformation only on the boundary, you will find that it remains the same exactly for these SL2R transformations. And that's why it has to be the Schwarzschild. Couldn't have been anything else, as Maldacena explained.
Can you go back to things where you had the two currents?
Yeah, in fact, I was going to.
Right.
Yeah.
So the additional term, the log.
Yeah.
So that was not known before.
It was not known before. And
The first two terms are known. The first is the Hawking term, and then the next one.
this is also the Hawking term. It was known to Hawking. I mean, they never wrote it down, but if they just solved those equations and did some algebra, you would have gotten that term. It was implicit in their equations. They never did the low temperature expansion. In fact, I don't know if anybody did it. I only did it like a few years back. I started understanding it's already there. It's just a very trivial algebra. Go on.
So the next term is there.
The next term is new. I would say the first person to write it down, I don't know. It's hard to tell, but certainly in the context of the SYK model, the first person was Bagratz, Kamenev, and Altland, who wrote down this thing. The fact that it appears in gravity, I think, was probably first stated in Maldacena and Stanford, and also Maldacena, Stanford, and Yang. The fact that it's exact was first shown by Stanford and Witten. And that's actually important because it's only because it's exact that you can trust the cinch. And now, from in the work of Shankar and Stanford, they've gone to even many other much, much smaller terms they've included from wormholes, and that's what led to this understanding of the page curve of one of the important ingredients in the understanding of the page curve of black hole evaporation. That came from just going further along this perturbation theory, not just this one. And then you have multiple space-times of more complicated topology. Yeah. Those corrections are e to the minus n for the SYK model. We don't really care about them, except when you're computing things like the spectral form factor and time autocorrelation functions. Okay, but for the entropy, they're just totally unimportant. Anyway, so now I have not much time. But let me at least say this. So let me go back to the random TJ model, where the Schwartzian already at n equals infinity has something useful to say, the h equals 2 mode. This is not really the Schwartzian path integral, just the large n theory. So Antoine talked about this TJ model, and he showed a certain mean field theory of the TJ model, which is justified in a certain separate large M limit. Notice here, so this is the model with fully connected cluster. N has gone to infinity. N is infinite. It's still not solvable. This is still a very complicated theory. So you have to bring in a further parameter. And Antoine described an approach where you just condense the slave boson. So there's another approach that we've been playing with recently, and also actually was looked at many years ago by Peter Wolfler and Christian Haule and others, where you do this decomposition that Antoine described, but now you do this decomposition by taking a double large M limit. You put also an index on the boson, which goes from M1 to M prime. You make M proportional to M prime, and then send M to infinity. That gives you a very well-defined set of equations that you can solve. These are the equations right here. You can see they're exactly these equations, except there's some indices of F and B, but there's always sigma as G cubed for both the boson and the fermion. All right, so these equations, we wrote down this form several years ago. We did the usual asymptotic analysis that Antoine has already described to get power law singularities and so on. But there was a surprise. In the end, there is no substitute to solving these equations numerically. And this is what my three collaborators, Main, Darshan, and Maria, have done. Incredible job doing it both on the real and imaginary frequency axis for all doping and temperature, and making sure everything agrees. And when the dust settles, we get the following phase diagram. There's in fact no Fermi liquid phase. So the Fermi liquid phase that Antoine found in the different large M limit just is not allowed in this large M limit. And in fact, the solution for essentially the entire range of doping at M equals infinity is a critical state in which effectively the J term is not important. The T term is much more singular than the J term, and this gives you a critical state in which the boson doesn't condense. All right, I don't want to go into the details of this. I mean, it's very similar to the SY solution, but it's a different version of it involving both bosons and fermions.
It's also very similar to Weber-Sprung-Kondo model, as it seems.
Yeah, I guess so, right. Anyway.
You have to keep a ratio and then prime fixed?
Yeah, we fix it at 1/2 because that's the physical value, but you can take any other value. At finite M, there is a, phase transition to a spin glass order, which we can deduce just as before. It's also e to the minus square root of pi m. I don't know if it's square root of pi, but anyway. But the thing you find in this critical metallic state is that the electron correlation function has a Fermi liquid-like form, 1 over tau, but the spin correlations have a continuously varying exponent. And if you look at the data that I think Antoine is going to show you for SU2, it does look like that this might be consistent with the numerical data for SU2. But anyway, but the reason I want to mention this now is that all of this work for the Schwartzian, it gives you an immediate dividend, and in a rather trivial way. Once you have a conformal solution like this, then we know that all the leading corrections are down by 1 power of energy scale. So Green's function has a 1 over tau. And now another important point, okay, this should be changed here. There's an error here. And the important thing is that this decays as 1 over tau. So if I take this 1 over tau and compute the resistivity, you'll just get a constant in this random model, random exchange model. So what is the correction? Well, to have any temperature dependence at all, you have to take the H equals 2 mode. So very generically give you down to 0 temperature a correction that's linear in temperature. That simply comes from the scaling dimension h equals 2. That's all. And so that's one possible contribution. There could be others. Could be other operators in this theory. We haven't fully analyzed all the set of operators. Hopefully that'll be done. Anyway, so there is a route to getting at very low temperatures a strange metal with linear T resistivity in this limit. So I can add one more line to the benefits of the Schwarzschian, is that it gives you a linear T correction to the resistivity in certain models. It's a small correction to the background resistivity, but nevertheless, it's nice to have a model that gives you something linear T down to 0 temperature. I'm not aware of any others where you can analytically show that. Okay. All right, so that's really all I want to say about TJ models, SYK models, black holes. And on the left-hand side, these are all models which are in the large dimension limit, either fully connected clusters or high-dimensional lattice with random couplings. I don't mind the random couplings. As you see, I'm going to argue next week that it may well be that random couplings are essential to get a strange metal behavior down to 0 temperature. But what's the more drastic approximation we're making here is that we're going to some large dimension limit. And in fact, there was a picture Antoine drew here where he had the vertex corrections just disappearing. That's okay in large dimensions, but in 2 dimensions, it's not at all clear that vertex corrections are unimportant. Okay. So to address that question and what happens in 2 spatial dimensions, as I said, there has been another approach, which is by Leon Balance and collaborators that Antoine mentioned in his talk, where you just take a bunch of SYK models, think of each model as a big atom, and put them on a lattice. So that's a very interesting direction, but it has the problem that it only gives you bad metal. It doesn't give you strange metal. There's another class of models that people have been looking at in the last 5 years or so, which are these, what I'll call the Yukawa SYK models. These are not just models of fermions with interactions. So you have a kinetic energy and some 4 Fermi term, and then you're playing around with that. These are coupled models of fermions and bosons. And so you have some fermion psi, you have some boson B, and then you have a Yukawa coupling. So all the fun we've had with SYK models of various types and various flavors with lots of random couplings, you can play the same game for this model too. And there's a very long series of papers who've addressed different types of these Yukawa SYK models. Probably the first one was this paper I wrote with Gayoto and Maldacena and my former student, Wenbo Fu, where we found this model appearing naturally when you try to supersymmetrize the SYK model. It can be rewritten as a model of this type. So it's also dual to a black hole, but a slightly different UV structure there. Anyway, so what's turned out to be very fruitful, and this will be the topic of my last lecture, is to transfer the insights from these Yukawa SYK models to more realistic models. These models turn out to be much easier to reduce down to lower dimension in a very realistic way. And I'm quite excited about the progress we've made by such an approach in recent work, where we think we now have a semi-realistic model of a strange metal down to 0 temperature in a very generic 2-dimensional situation without infinite range interactions or high dimensions or dropping vertex corrections. And what's made that possible are really all the insights that came from solving not the original, well, SYK too, but for this work, more important has been the Yukawa SYK models. So I think I'll just leave it there, and next time I'll talk about a realistic version of Yukawa SYK models.